So moving into section 6.1, we are looking at what are called oblique triangles, where an oblique triangle is any triangle that does not have a right angle. To get one of these, there are a couple of arrangements. Either we can have a triangle with all acute angles, all angles less than 90 degrees, or we can have one that has two acute angles and one obtuse angle. But the point is, nothing in here is 90. And we still want to talk about them, but the problem we have here is if we look at stuff like this, there isn't a direct way to use all the stuff we saw in chapters 4 and 5. There isn't a direct way to talk about trigonometry because the rules we have for trigonometry are all built around right angles. Well, if we have something like this, if we have something that doesn't have a right angle in it, we can instead talk about a thing called the altitude or height of the triangle, that we can take something that runs from one of the angles down to an opposite side direct through at a straight line to make a 90-degree angle, and thereby have ourselves, in a sense, two right triangles that we can work with, that we can pull out from the oblique triangle that we're working on. And from there, we can talk about what's going on with those in terms of sine. That is, if we look at that altitude, that height, and give its length h for hopefully obvious notational reasons, and then look at sine of a, we can treat that as a right triangle in terms of h. So we will have that the opposite side is h, and the hypotenuse for that is b. So we get sine of a equals h over b. Meanwhile, on the other side, if we look at it in terms of b, we could say that sine of b is equal to h over a. Now, okay, that doesn't tell us a whole lot, but if we take this and we multiply over these values, those constants, we get two equivalent ways to write h. That is, the height can be seen as either b times sine of a, or a times sine of a. Sine of b. It'd be very nice if it was a sine a, but we're not quite there unless we're going to rename these whole things, and well, that'll throw the whole system off. But we have that where, more usefully, we really have these two relationships. And as a result, since we have that b sine a equals a sine b, well, we can just divide terms over. That is, we'll divide over a sine a, and we'll divide over a sine b to get that a over sine a is equal to b over sine of b. And in fact, if we want to, we can do something similar where we'd put our altitude or height in a different place. We'd jut it out from either angle A or angle B. If we do that, we could also get that this is equal to c over sine of the angle c. That is, the length c over sine of the angle opposite to it. And this construction right here, this set of equalities, is what's called the law of sines, which gives us a general description for the relationships between side lengths and angle measurements for opposite sides and angles. Makes sense for sine. Sine is opposite over hypotenuse, after all, in terms of any triangle. This can actually work for right triangles. It's just it's a little bit less interesting for right triangles. But essentially what we have here now is a way that we can connect all of these pieces. So if we want to be able to find the measures of certain angles or certain side lengths given others, as long as they're in the right arrangement, we can figure that out. Which is what we're going to see next. That is how we can solve certain kinds of oblique triangles using the law of sines.